Hello, everyone, and thanks for showing up this morning or this afternoon or this evening, wherever you happen to be. And welcome to your daily dose of DOE here at the 2020 online DOE Summit presented by Statties. And today we have the pleasure of having Dr. Geoff Vining give us a little talk about innovative mixture process models. And I'll give a little introduction here to Dr. Vining. I won't go through the whole thing, but you can see it all here. Dr. Vining is a professor of statistics at Virginia Tech and also the founding chair of the International Statistics Engineering Association, also known as ICEA. And you can read the rest there. And what he's going to do is have a little talk. We're going to have a Q&A session at the end. So if you have questions during the course of the presentation, simply type them into the questions section that you see on your menu on the right-hand side. And you can type them up, and then when we get to the Q&A section, I can go ahead and read them through to Dr. Vining, and we'll have a conversation from there. And so now I will introduce Geoff Vining.
Hi, everybody. Everything to work here. So can you hear me, Greg?
Oh, yep. You are coming through loud and clear.
Okay. Am I showing my screen at this point?
You are showing, yes, you are. We are seeing the GoToWebinar page right now. So it looks like your web browser. There, whoops, there we go. Now we see the
perfect
presentation.
Greg, thanks for that introduction. I'm very pleased to be able to give this talk. It's fun to talk about these designs. I'm very pleased that they've been implemented into Statties in Design Expert. So basic structure of my talk, I'm going to give you the story behind it. I think it's always important to understand that these things just don't pop out of any place. And there are kind of some fun stories associated with this. And then I'll go through the kind of thought processes behind the model and the design. They go hand in hand. One of the keys is that John Cornell was part of this group. And, you know, John was Mr. Mixture. We had to sell John on this, and that's part of the fun of the story. I want to make sure we understand the analysis because it is subtle, and I'm very pleased that Design Expert does it absolutely correctly. So this is always very good. And then I have an example. It's a recent one that I've been doing here with a project at NASA in terms of reliability. So it's a computer experiment. It's an actual KCV design, an actual KCV analysis. I can't go into the details about what the response or what the actual factors are in the experiment, but it's nice to be able to see how this all works and to illustrate it. So without further ado, the background on this is a Virginia Tech connection. So my PhD is from 1988 from Virginia Tech, and Ray Myers was my dissertation director, my advisor. My first academic position was right after graduation at the University of Florida, and John Cornell and Andre Curry were members of the faculty there. So John got his PhD in 1968. John's interesting because he was the second graduate student in statistics at the University of Florida. So that was about 65 or 66, I think. Lehman, I forgot who the first one was, but that's okay. John, after he graduated from the University of Florida, worked for Tennessee Eastman, now Eastman, for about a year and a half. Both he and his wife were very much Floridians, and they found Kingsport a little cold, and they decided that maybe they wanted to go back to the University of Florida, but John needed a PhD. So Ray Myers had just published in 1966 a paper with Bill Thompson on mixture experiments. And John was very interested in that from his work at Eastman. So he went to Virginia Tech and was hoping to work with Ray. I can't tell the story on why he didn't work with Ray, but he wound up working with I.J. Good, who's one of the most distinguished statisticians in history. And I.J., I think, only had 3 or 4 students. John was his second. Andre was interesting because he had 2 PhDs. His first was PhD in mathematics from Florida, the Florida connection, but then he decided he couldn't get a good university job as just a mathematician. He was from Syria. He had gone to Lebanon with his new wife, and they decided they wanted to come back. So he came back as a PhD student at Virginia Tech, and Ray was his advisor. So John was really trained by Ray in terms of all that we're going to talk about, even though IJ was his advisor. Andre and I are officially students of Ray. Doug Montgomery, many of you may know, I'm sure are familiar with Doug because of his books on statistical process control and especially for design of experiments. Doug's degrees are all from Virginia Tech, all in industrial engineering. So that's the reason why Ray was not his PhD advisor, but worked very, very closely with Ray. So we all have this tie back to Ray Myers and to Virginia Tech. And part of this is I was teaching short courses for Doug, which is part of the context for why this set of experiments, this experimental design technique evolved. My initial work actually came out of my experience just before I went to graduate school, working for a writing instrument company, Faber-Castell. And there was a problem on the line with an injection molding process with the fit of the cap to the barrel of pins. And that I thought was a solved problem in 1985. I later discovered it's Taguchi's robust parameter design. It wasn't a solved problem. And I happened to be in the right place at the right time because of the Taguchi phenomenon. But it's an experimental strategy which you have control factors, which are the things you can control in an experiment, but more importantly in a process. And then you have noise factors. And the noise factors are things that will contribute to the response of interest. You can control them usually quite well in an experiment, but they're actually random in the process. So they're generating noise. And the Taguchi approach was a crossed experiment with an experiment in the control factors with another experiment in the noise. And that's going to be important for us to understand how John Cornell used to approach mixture components and process factor experiments. John, when he heard about the Taguchi approach to design, the robust parameter design, his thought process immediately went back to how he worked with mixture components and process variables. Hence, my background here, as I learned what John was doing, I could translate and we could communicate. My initial interest was efficient analysis of results, and I was really lucky. The very first paper I ever published won the ASQ Brumbaugh Award. It's been straight downhill from there. It's been my most cited paper. It's amazing. I was very lucky. So after I was at the University of Florida, I was working with my mentors. Andre and John were my official mentors within the department at Florida. Clearly, we had the tie back to Ray. So there's a nice paper from 1992. Originally, that was Curry and Vining, but Andre and I couldn't exactly agree how we should approach the alternatives to Taguchi. So we brought Ray in as the kind of the referee. And of course, we both deferred to him. So he was the first author of that paper. I won't go into all the stories about that one. That was an interesting time. And then I did some work with John on evaluating mixture predictive capability. My dissertation under Ray was not on robust parameter design. It was actually on graphical approaches to evaluate experimental designs. And so we started translating some of that work to the mixture experiments. So I was learning mixtures from the expert. I was working with John, and it was really very, very fascinating to see how it's similar to response surface and how it's slightly different. And those subtleties are really, really important. And I greatly value that time with John. John and I he was my best friend in Gainesville, not only just from the department, but from church. So it was very meaningful for me. A very famous data set for John was his fish patty data. Apparently it's the Burger King Whaler sandwich. So it was a mixture component of 3 different types of fish and 3 different process variables. And the idea was how to come up with a mixture of the fish that would be robust to having teenagers fry it at Burger King. And it's a crossed experiment. And the way John would approach this is if he had to fractionate the experiment, he would always fractionate the process experimental factors. The mixture components, the mixture basic design was sacred to John. And that's important as background for how we were approaching this with this KCV designs. So the actual origin of this is I was teaching these short courses for Doug Montgomery. I was working at an adhesives company in Columbus, Ohio. Was just teaching a short course where I introduced how to do experiments with mixture components and process variables direct from his notes, which were largely based on John's first edition of his mixture book. And in the example that I had to work through with the people at this adhesives company, they used the ratios of the mixture components, not the usual way John would analyze the experiment. I know Pat really likes the ratios, and there's some strong reasons for using the ratios. It begins to look more like a true response surface design. We really needed to build second order surfaces. The ratios are a great way to do that. But the resulting design wasn't efficient because it was focused on the rays in the space formed by those ratios. So it was very limited in how it covered the experimental region. And of course, I was working with John and understanding how the experimental region was critical to how well you can estimate the model. The better you could spread the design points over the experimental region, the more efficient the analysis. So I saw a disconnect. And Scott Kowalski was just beginning his dissertation. I was his advisor. So guess what? Scott got to deal with these experiments. And he did a great job with this. There's some basic issues here. In John's world, as I said, he really viewed the process variables very much like Taguchi noise factors. They weren't the primary interest. And ultimately, when you really worked with him, once you got him to this point, the mixture process interactions were less important, even though his models would allow you to estimate every interaction in the world. I'll come back to that. But he really was viewing the process factors as the noise. And I said earlier, if you're going to fractionate for John, you fractionate the process variables because that's not at the primary interest. He wants to see what's happening with the mixture. Part of this is a reflection, and it's still prevalent in a lot of organizations, of the research and development groups and the production divide. In a lot of companies, corporate R&D owns the formulation. They do it in a pristine lab. And I'd love to hear comments from people listening to the talk. If they still see this divide, I still see it in the work that I do. So corporate R&D owns that formulation. They do it and maybe into a pilot plant, and then they send it down to the production facility and say, okay, here is the formula. It's sacred. You don't touch the formula. Now you figure out a way to operate your process to generate this so we really make money. And, you know, in some cases, it would be great if the people who actually have to make the product could understand how to tweak the formula to improve the actual production of the material. And that requires the interactions between the formula and the process variables. And that's one of the beauties of what we're proposing, what we proposed with the KCV designs and models. Here is how John would view the experiment. I love the way John would do the graphics. So there was one to the left. You see it as the simplex from the mixture components. And then you would have an experimental design in the process variables at each one of the locations of the simplex. An alternative way to view it is on the right. You've got the 2 to the 3, the 2 cubed experiment in the process variables. And then you can see you doing the mixture simplex at each one of those locations. It's a true cross design. And that's fundamental to how John is approaching this. Very similar to the Taguchi robust parameter designs. And I said, this is all happening at about the same time. So I hope you appreciate the thought processes that are going on here. John loved interactions. And here is that full model that he would have been using. He did use at one point for his fish patty data, which had 3 mixture components and 3 process factors. And notice you don't see Z's, and we'll be consistent with this. The Z's represent the process factors. The X's represent the mixture components. John loves every possible interaction he can create. Notice you don't see a Z squared term in there anyplace. Okay? John doesn't think that way. He likes interactions, even up to 5th order, even up to 6th order on that bottom line. John loved interactions. And that always was kind of an interesting point working with him in the response surface world, because he didn't fully appreciate the Taylor series approximation. I remember a paper he published with Doug Montgomery in the Journal of Quality Technology looking at interaction models and lots of interactions. That was John's world. When you understand the Chaffee model, with that Chaffee model, the higher order terms like the Z squared terms disappear. John's world with the mixtures was very much interaction focused, and it was because of the consequence of the mixture constraint. We'll talk more about that. This is what how John would approach a fractional factorial experiment. Again, this is direct from the 3rd edition of his book. So again, notice it's really focused on the interactions. We don't see that traditional, the Z squared kind of terms that we would be expecting from traditional response surface. Not how John thought. Here is an example where John would fractionate. So on the right-hand side is, I believe, the positive fraction. It is the positive fraction of the 2 cubed run at each location in the simplex for the mixture experiment. And then the right-hand side has the negative fraction. So now what would happen here? Let's suppose that, notice that if we could project down, okay? So if there wasn't a real difference between A and B, what we would wind up doing is projecting all of this, the full 2 cubed, onto each one of the locations of the simplex. Projection properties are important to me. They were very important to what we were doing with the KCV design and the models. And I want us to appreciate that. That's part of the beauty of the design. A common reduced model, this is the way John typically thought about it, and this is an extension of the mixture amount problem. So John often really thought about these process variables. Like a classic example is the amount is a process variable. So this is really how John was beginning to think about it. And, you know, here is the basic model that he would be running on this, because, you know, well, this one had no mixture by process interactions. And that's the typical way he would approach the mixture amount problem, because it's noise. He's not interested in the mixture by the noise interactions. They're not of interest to him. And you saw, you see a lot of the software not fully appreciate what's going on here. Design Expert does, which is something I really like. And one of the reasons why there are no mixture by process interactions is that they're already encountered in there. So that 1 degree of freedom that's associated with gamma 1 Z1 actually is representing the interactions of each one of the mixture components with the process variable. And that's important here. So what is in the upper part of this slide up here here, I can point. Up here, what's 1 degree of freedom in this model could be expanded to 3 degrees of freedom here. Of course, that's going to lead to interesting aspects about how do you do the test. I want to talk about that down the road as well. So here we are. I'm working with Scott, and we're getting ready to have committee meetings. And Scott was my guinea pig. My wife is Peruvian, so I don't know how many of you are familiar with the favorites. One of the most famous aspects of Peruvian cuisine is cuy, and they love cuy. Cuy is guinea pig, so just keep that in the back of your mind. So poor Scott is my guinea pig on how I like to mentor PhD students. I hate being on a PhD committee and there are only 2 meetings, proposal and final defense, because usually the presentation is painful, the exam is very long, and nobody's happy at the end. I prefer to have lots of short meetings with the committee and keep them actively engaged in the research. I like it when the committee members are co-authors on the papers. That's one of the objectives behind it. Also, my colleagues like it a whole lot better. It may sound like it's more work to have 1 meeting a semester instead of having 2 meetings over 3 years, but they find that it's short, everybody understands what's going on, and they could see how their concerns and their questions are incorporated in the research as it evolves. So the focus is on collaboration, and the thing is to get past formal examinations. And I like that because it takes pressure off the students, because it's not all of a sudden it's an up or down decision on do you continue or not. These are conversations, and one of them we turn into the proposal. And then by the end of this, we should all be on the same page that this is good research, it's ready for publication. That just makes the final exam a formality. Well, Scott was the first. My colleagues were not used to this, particularly John. John liked to be combative in PhD exams. So preparing for John was critical. We had to sell this to John. I knew John would like the idea if we could get him to listen, okay? So that's part of the story here. So our presentation structure, we're going to start with a true second order model in both the mixture and the process. That's the beauty of the model we're using. I know that Pat really likes that, and it's cool. Then we show the impact of the mixture constraint. So it emphasizes that what looks like an interaction model is actually reflecting the full second order complexity, but we're restricting the model to what would be an appropriate second order Taylor series. We highlighted the resulting model, and then we were going to show figures of the proposed design strategy and then emphasize robustness of the design. So I'm jumping ahead to the next slide, but what's going to happen here is we started with the true second order model in both. John was holding his tongue. We showed the impact of the mixture constraint. He was good with that. I mean, this is his world. Then we highlight the resulting model. Well, this is what that model looks like. And it's actually, in this case, a special cubic, because we've got the 3-factor interaction, 3-component interaction. We can actually fit that. I mean, John really loved that. So that model's up on the board, and next thing you know, oh, and if there are no mixture process interactions, it collapses, okay? So, you know, this is the basic model for what we were doing, second order model. It's a true second order model and everything. Okay, well, John's reaction. First, John, this was a formal examination, so he was out to kill bears. He jumped to the board once Scott proposed the model and made clear we're going in the wrong direction, absolutely the wrong direction. Fortunately, John and I are very good friends. I'm junior, very junior, and I just simply say, I'm brand new associate professor. I say, John, just sit down, literally like that, just sit down. And he did, and he did. That was cool. And then Scott presented the basic design structure. And this is it from our technometrics paper. So this was an easy one for me to steal. In the technometrics paper, we do it as a split plot, but the structure it lends itself either to a split plot or not to a split plot. Key idea, John historically would fractionate the process variable design. We're fractionating the mixture components. Oh my. One of the big reasons why the design size explodes when you do mixture by process variables is the mixture experiment, not so much the process variables. So here we've got, I'm highlighting, okay, that's the 2 squared in the process variables. Each one has a mixture experiment. Notice if Z1 is unimportant, okay, this collapse over here, oh my, it's a full mixture experiment. This collapse over here, it's a full mixture experiment. We truly have fractionated it. It's John's idea, but we flipped it. Rather than fractionating the process factor experiment, we're doing it in the mixture components. There are big design savings from this. We're interested in fitting a second order model. So this was a basic strategy that Scott and I derived. So we would have the axial points would just be at the centroids of the mixture experiment. And then we would have the complete mixture experiment in the center. Many variations of this. This is what we recommended as our kind of KCV basic design. So it's tied back to the model. This design supports that model very, very well. But more importantly, it respects what happens if terms are not important. That's why John hated optimal designs for mixture and process variables just based off the model. Because what if a term isn't important? What if one of those process variables is unimportant? How does this thing preserve structure? An optimal design is optimal for the model for which you're trying to fit. That doesn't mean it would be optimal for a subset model if some of the terms are unimportant. This was guaranteeing good structure if a process variable was not important. That was a critical contribution that we were making from this whole approach. So John's saw it, wow, okay. As I said, he was expecting a blind optimal design application. We didn't do it. It was a radical for him. We fractionated a mixture portion, but he saw the projection properties. Ooh, and he saw the benefit in overall design size. John was the second author on the 2 papers dealing with mixture and process that came out of Scott's dissertation. He had 4 papers. We were also doing split plot work as well. Traditionally, papers that come out of my student dissertations, the student is the first author, I'm the last author, co-authors are in between. John gladly participated in the writing of the papers. We sold it. That was really, very important. But we had to get him to see a different perspective of a problem he had lived with for many, many years. Getting back to the analysis of that mixture process interaction, we got to do a test for the mixture process interaction, and we're looking at whether those gammas are all the same or equal to what would happen if we just didn't have the interactions. Gamma 1 would be the coefficient associated with Z1, okay? If we ignore the interactions, so gamma 1, 1, well, that's looking at mixture component 1 interacting with Z1. Mixture component here, sorry. This is looking at mixture component 1 interacting with Z1. This is mixture component 2 interacting with Z1. Here is mixture component 3 interacting with Z1. That's the null hypothesis, that they're all the same effect. It's just like the test on a single mixture component, okay? And Design Expert is really good about this. It locks it in. If you're looking at the test on a pure component, you don't compare that to 0. And in fact, Design Expert is good at hiding how to do the test, but it's a test back to average. So ultimately, this test reduces to comparing one of these to the average of the other 2. It's a basic 2-sample t-test. And there are ways to automate that, but that's the idea here. So it's not a trivial aspect in terms of the analysis. You got to put this in here. Design Expert does a very good job of that. So the result of the basic mixture constraint, you got to have the pure blend terms that are required. All of you who play with mixtures on a routine basis understand the Geoff model. If you got to have it in there, you can't drop it because you got to move all of the components simultaneously. You just can't ignore one, say it's 0. If one mixture process interaction is important, then the model requires all of those interactions. Otherwise, you're dropping out parts of the process variable, and that's not really wise. That could really impact predictive capability. Once again, the KCV models are truly second order. They can be higher for the mixture components. That special cubic term is very popular. One of the nice things about this is it's got better interpretation than the traditional Geoff models, particularly those that John had been proposing. Pat likes it because it's combining some of the nice features of dealing with the ratios of the mixture components from the modeling perspective, but it's giving better use of the design region. So here we come to a real experiment. This is one that we actually did about a month ago, so timing was impeccable. I've been working for a very long period of time with carbon overwrapped pressure vessels. Most of you have heard of Apollo 13. Some of us lived through Apollo 13. That was a metal pressure vessel that went boom. Now it killed the one next to it. It did major damage to the third, and there are only 3. So carbon is stronger than steel, lighter than steel. Also, it doesn't produce shrapnel the same way. So the dominant form of pressure vessels on spacecraft are carbon overwrapped pressure vessels. NASA is very keen on what is the expected life over a mission for these pressure vessels. There are 32 or 33 carbon overwrapped pressure vessels on the International Space Station, one of which is extremely critical. Most of the funding for the work that I've been doing on these reliability experiments has come from the International Space Station. This is a real experiment, and I can't really discuss the details, so sorry about that. NASA has marked this as sensitive but not classified. Those of you who are familiar with export control regulations and international traffic and arms regulations, that's what NASA would call sensitive but not classified. So I wish I could go into more details about how cool this experiment is. I can't, and I apologize for that. There are 3 mixture components, and I'm going to call it STR, SRH, and SRL. And these were decisions made by the engineer on what would be the ranges we want to look at. This is a computer experiment. It's based off physical experimentation, but we're trying to do something very interesting and very new, so we've had to do it as a computer experiment. So for STR, bounded between 0.3 of the number of items. The process variables are the number of items, I'll tell you that. So, when we say that STR is 0.3, 30% of whatever we're doing in terms of the total items would be STR, okay? And similarly for the SRH, there was a lower bound of 0.1, upper bound of 0.7. SRL, lower bound of 0, we could go all the way to 0, up to 0.3. So we had items as one process variable, so it's a mixture amount problem, for those of you familiar with that. And test plan was categorical, and I can't go into the test plan at all. So sorry about that. But this is a very nice scenario. We needed to explore this space. I was dealing with engineers who wanted to do the shotgun approach, whatever looked like a good thing to try to test. That's how they did their testing. I said, this is ridiculous. We got to be more structured. It was a great opportunity to pull this out of my bag of tricks. And again, I'm so happy that StatEase has it in Design Expert. Here are plots of the results. I cannot tell you what that response is. Sorry. But one of the nice things here, and one of the reasons why I really like this particular application, if we go back earlier to how we were looking at, okay? Now, if you've got lower bound constraints, that's the simplex is preserved. If you have upper bound constraints, you got an flipped over simplex. But in the real world, a lot of the experiments, you got upper and lower bound constraints. And as a result, the resulting region for the experiment in the mixture components is no longer a nice simplex. And we're seeing that in this particular case, we've cut off, the vertex with the SRL component. So it's an irregular polyhedron, and I like that. The focus of this, how we did this was going back to the original paper. We fractionated the design in terms of the mixture components, with the vertices being one experiment. So here are the vertices, midpoints of edge, the others. So these two are items at the low level. These two are the items at the high level. If there's no difference between the low and the high with the items, bang, it projects down. It projects to a complete vertices and midpoint of edges experiment for holding items at whatever value. Really cool. Once again, looking at the top versus the bottom. Here is the experiment with the midpoint and the edges. Here we have the vertices. Here we have the vertices. Here we have the midpoints of the edges. If there are no differences between the test plans, oh my, surprise, surprise. There's no differences. This thing collapses down. That's the beauty of the experiment. And we are expecting some terms not to be important in here. So we walked into this expecting that we would need to go with a reduced model. Look at the beauty of what's going on here. The response is something we want to minimize. So we can see, just looking at the plots, what are lower numbers if we have more items, surprise, surprise, than we have less, and that there are certain regions where we're beginning to see really, really good performance. Oh my. We can almost analyze this directly from the plots of the results. There was an interesting question, however, and we weren't getting the model fits that I wanted, so we augmented this design. But we were working with the engineers with the visuals, because they understood the visuals. They didn't understand the models. That just clouded things. The visuals were really persuasive how to analyze the experiment. So we were doing modeling in the background. I taught them how to optimize off of that, but their real analysis was much more focused on the visual. They understood it better. So we did look at a middle value in the number of items being tested. Now, the midpoint between 75 and 150, okay? So 75 was the low level. I was 150, is 112.5. It's kind of hard to have a 0.5 of an item. So we made a decision. This is a computer experiment. We're not going to put it at the exact center. 110 was roughly there. And we actually used that true coded value. We did not analyze this in Design Expert at the time, but I do have analyzed it in Design Expert, and we treated it as a 0 value. It's not quite 0, which is fine, because I can show you analysis now that I couldn't show you otherwise. Here are the results for that kind of middle value for the number of items. Okay. Once again, we can kind of see this is where we're getting really good results. Okay. That's not inconsistent with what we saw over, okay, particularly. The engineers were very comfortable with the graphical analysis, but we did need to do formal optimization, so I'm building the models in the background. Here it is in Design Expert. So going through, we've got the structure, okay? So that's the pure blends, A, B, and C. D is the number of items variable. E is the test plan, categorical variable. So linear mixture, it's the thing about that. So we look at the AB and AC interactions. Okay, so these are the mixture component interactions, and we see that they're important. And we begin to see now AD, BD, and CD. Okay, I've broken up the impact of the items to these three interactions. We'll notice that there is a definite interaction between number of items and mixture component A. Okay, we see the same thing for mixture component B. We see the same thing for mixture component C. So there are definite interactions, and we need to have that. And remember, once you have one, you have to put them all in the model. So that's important here. Looking at the mixture component interactions with the other process variable, we have AE, doesn't look like it's very important. BE, not great. CE, I definitely would count as important on this. This is a small experiment, so I would be using a 0.10 cutoff value. So the decision we made was we want to go ahead and keep all of those interactions. We think that that CE interaction more than justifies us to do this. And so that's the basis for the model. Okay. I like this because design experts giving the VIFs. Got to be careful with variance inflation factors because the mixture components are inherently correlated. Okay, can't get around it. The experiment was planned that way because of the mixture constraint. Generally, I'm more looking at what's the impact on the process variables. That's where I've been most interested. So again, this is just going back to what we saw before, but it's got the confidence intervals and the variance inflation factors, which I like. Normal probability plot of the residuals. This is a computer experiment. There is noise in here, so it's using some bootstrapping. So this is not completely deterministic, but there's the normal probability plot of the residuals. I'm very happy that Pat and Mark went ahead and put in the externally studentized residuals. Those are the proper residuals. I was very glad that they did that. Here are the residuals versus the predicted values. We're not seeing any major problems. I had problems entering the data, and actually filing the problems with the diagnostic plots helped me correct my mistakes inputting the data. So data cleaning is always important. We do begin to see a little less variability at the low level for the STR. There are reasons for that. I can't talk about them. Similarly, we have less variability at the high level for mixture component B. There are reasons, can't talk about it. Similarly for C, okay? But I mean, here's the standard analysis from Design Expert. Residuals for items, and that doesn't look too bad. This is off-center because it really was off-centered. And here it is for the test plan. And we see a little more variability at the low level than we have at the high level, nothing to get really excited about. Here is the contour plot, and I'm colorblind, so that always gets to be interesting. It's not as helpful for me, but again, the engineers were looking at the contour plots. That's how they were trying to make their decisions, quite frankly. So this is very consistent with how we were working with engineers for actually how to do the analysis. And here are the formal optimizations, and it's coming up to this point up here. Here it is in terms of desirability, but we only have one characteristic. So the desirability is matching exactly what we were trying to do with the prediction. So surprise, surprise, this is the area where we want to work. It was counterintuitive to the engineers. This was a complete surprise that we needed to be working in this kind of area over here. So surprising result. We're still working through those consequences. I know I had an hour, and I've got that we're at 10:48 Central Time. Just some final comments. You know, the KCV models and designs are really a very powerful approach to dealing with the mixture process problem. Model form is very flexible. The design strategy is intended to make efficient use of the design space, has nice projection properties. I like the original design strategy that we did in the paper. Of course, we're clearly biased to that. design expert will allow you to do that through the candidate point list. They'll also come up with an optimal design, and that's fine too. I want to emphasize, sometimes we don't think about mixture and process variable designs as appropriate for computer experiments. Surprise, surprise. Yes, they are, okay? And design expert handles it very well. So with that, I'm very thankful that StatEase has asked me to be able to speak today. I hope you learned a little bit about the background on the experiments and some of the personalities involved. But otherwise, Greg, I'm ready to turn it over to questions. Do I need to do something?
Oh, nope. I've got it here. Sorry, I was muted and forgot I was muted. So, thank you, Dr. Vining. I appreciate the talk. Here, let me share my screen. Actually, should be right there. Okay, that. And let's see, get to a couple of housekeeping things, and then we'll get into some questions. For your benefit, for the attendees' benefit, we're running a special offer on our distance learning workshops, 25% off. You'll also receive this information in a follow-up email. But here's the code. One thing to keep in mind that the code is valid until the end of August, and it's for courses that you attend before December 30th. A couple of other notes. The slides from this presentation are now posted up on the StatEase website under the webinar section. And also we will have the recording posted in the same place probably within 24 hours. So next, let's get into some questions here. As I mentioned, you can type your questions into the little questions area on the right-hand side of your menu. Let's see here. Well, first of all, early in your presentation, Dr. Leonard Lai said that, Geoff, that you were too humble. Just thought I'd throw that out there. Let's see, next.
My wife would never believe that statement.
Okay, let's see. Question from Paul Nelson. Hi, Paul. Let's see. What therefore comes first in Geoff's mind, the graphical structure or the model? I love the visualization of the structure he provides.
We started with the structure of the design. I mean, that's kind of how I think about it, and then make sure that it would support the model. They go hand to hand. It's kind of hard to separate one from the other. But in this particular case, after I had taught the experiment in Columbus, I'm on an airplane flying from Columbus, Ohio, back to Gainesville, Florida, and I'm drawing these designs on the cocktail napkin as I'm drinking wine. So I actually did start from the experimental design structure.
Okay. Oh, and he adds, by the way, corporate R&D for pharmaceutical companies most certainly own the formulation and transfer this to production for manufacture. Okay, let's keep rolling down here. Is the, let's see. And we have Arvid Harding at Eastman.
Hey, Arvid, we were classmates at Virginia Tech.
Awesome. Let's see, related to the example, since this is a computer experiment, what was the advantage to fractionating the mixture design? Was the number of runs critical?
Actually, it was, and it wasn't an immense amount of time to run this, but what we really were looking for was just general trends in what was going on. So we really did focus on going ahead and fractionating it. If we hadn't have done that, we would have wound up looking at almost every possible combination, and we were trying to save. As I said, I had colleagues working with me, the engineers who wanted to do shotgun. So all I wanted to do was give them a minimum number of points to provide enough structure for us to see direction. And I was confident that this would work, and it did. we didn't need the whole points to cover a very complex surface. What we were looking for is general directions. And that's one reason why the graphics became a great way to explain to the engineers what we were doing.
Okay. John Davies asked, I believe this is related, why are there no interior mixture formulation points in the NASA design?
Weren't of interest to us. We were expecting that where we wanted to be on the characteristic of interest would be on the boundaries. Now, it's important to remember that this is a true second order model, so we are getting the curvature. We still see curvature in the interior, but we decided that we really didn't need that point in there. Again, we were building off some prior insights about the situation with which we were dealing.
Let's see. From Gregory Perrine, what would be a situation where KCV would not work well with a, quote, fully, unquote, crossed quadratic times quadratic?
Well, this is a fully crossed quadratic with fully crossed quadratic. So I guess I'm not clear on the question.
Okay.
Completely crossed in the sense, now perhaps I may have misinterpreted that. So completely crossed then is going to create much higher level terms. So if you're talking about completely crossed, then you would begin to have pure quadratic terms crossed with the individual factor terms. So you're beginning to get third order terms. You're beginning to get fourth order terms. You can get even much higher than that. So if you're doing that, then you're going back to how John was originally approaching the problem in that 56 term model that he had proposed for the fish patties. So what we were trying to do is recognize that the likelihood of these, anything higher than a true second order term, other than perhaps that three factor special cubic term for mixtures, they seem to pop up frequently, just weren't likely to be present. And that's the reason why we were trying to be efficient. And for the NASA experiment, that was quite true.
Okay. Well, this is an interesting one from somebody you might know named Scott Kowalski. He said, the history was great. I will just add that Geoff and I consumed a fair amount of wine when coming up with these designs.
Oh, yeah. This was back when Scott was commuting from just north of Orlando to Gainesville to finish up his dissertation. So he stayed at my house. We had a great time. It was fun.
Okay, let's see. Let's get on to another question quickly. Ruben Mercia is asking, I'm assuming that KCV models are mainly for characterization. Is it possible to use them for screening purposes, main effects, and fewer runs?
I would think so, but we never thought of it so much in that way. We were so focused on being able to fit the second order surface. In some sense, the very first experiment that I showed, the 20 run experiment, was a little bit of the characterization. We weren't looking at quadratic terms in terms of the process variables, but we were looking at as much of the structure that we could get from the mixture experiments. So in that sense, we were being a little bit of screening in terms of the process variables. Screening gets to be more difficult when you're into the mixture experiment because it's not like you can drop one of the mixture components. So almost immediately you're beginning at a little bit higher level experiment than that. When you begin to do screening there, you're making a decision, do you have synergy or do you have antagonistic kind of relationships among the mixture components? So I think that's a very interesting question. What does screening mean when you have the mixture of process variables with mixture components? And you want to know the truth, I haven't thought much about that. So, but I appreciate that question. I think that's an interesting perspective that we need to consider.
Okay, let's see. I think we have time for a couple more here. Let's see. We have another question from Greg Perrine. does the power evaluation for KCV change versus a standard mixture process design? And does fraction of design space and design expert cover these models?
I really don't know if I'll go to the second one. I don't know if fractional design space has been applied to these models. I wish I could have the answer to that. I don't. Frankly, I haven't thought about the first question, so I have to admit that. So what were the first questions again, Greg?
Let's see. Let me go back. The first question, does the power evaluation for KCV change versus a standard mixture process design?
I don't think so, but I haven't looked at it that closely. And we did not investigate that in Scott's dissertation. So my instinct is it wouldn't be dramatically different, but I haven't looked at it. So sorry.
Okay, let's see. Okay, this is a question from Ashay MS. How to work out the process if there is a mixture with too many process parameters, e.g. solid dispersion of a drug by hot melt extrusion mixture?
Oh, that's an excellent question, and I haven't had to deal with it, but I would begin to try to deal with it at the highest level I could, which would be the fewest number of factors. Well, my first approach to this is to break it up into the system. And again, I'm not familiar enough with what you're describing there. You're just dealing with a mess. And
Yeah.
I haven't worked enough with that for me to be able to sketch a reasonable solution, but it's something that is very, very important. And I'm beginning to deal with similar kind of issues, not in the pharmaceutical realm and not with the formulation, but on experimentation for jet turbines, believe it or not. And there, I'm trying to take the approach of understanding the system, understanding each component within the system, being able to build models within those components, and then see how those all work together. I don't know if that would work for your problem or not, but that's when my thought processes have been most recently. So,
okay. There is a comment here from our leader, Pat Whitcomb, who made a comment about power isn't the right metric, use FDS, going back to that question about power.
cool. I'm glad Pat is there to support us.
All right. Well, I think that sort of wraps up our question and takes care of our time. So, Dr. Vining, thank you so much for being here and making a great presentation. We all appreciate it. Thank you very much.
Oh, my pleasure. And again, thank you so much for inviting me. This has been cool.
Oh, it's totally been our pleasure. And thanks everyone for stopping by and listening to the presentation. And we hope to see you back at another webinar soon. Thanks. Have a good day, good night, or wherever you happen to be. Take care now.